Facing an equation with two unknowns can feel like hitting a brick wall. You cannot solve for x if you do not know y, and you cannot solve for y without x. Substitution works by using one equation to express a variable in a different form, which we then carry into the second equation. This merges the two problems into one. Let's look at how this works. On screen, we have equation 1 in blue, x plus y equals 10. Below it is equation 2 in green, x minus y equals 2. We start by picking the variable that is easiest to get alone. In the blue equation, we can isolate x simply by moving the y to the other side. Now we have an alternate expression for x. It is 10 minus y. Next, we take that expression and drop it straight into our green equation. Wherever we see an x, we replace it entirely with the quantity 10 minus y. Look at the result. The second unknown is gone. We have collapsed a two-variable system into a basic linear equation with only one unknown, which we can solve using standard algebraic steps. Systems are rarely this clean in practice. Consider this new problem. Equation 1 is 2x minus y equals 7, and equation 2 is x plus 3y equals 7. It is tempting to isolate the first x you see, but that 2 in front of it is a problem. If we isolate that x, we are forced to divide everything by 2, which introduces fractions into our equation. To keep the math simple, we look for a variable with a coefficient of 1 or negative 1. In this case, the negative y in equation 1 is our best starting point. We make the y positive by moving it to the right, and then move the 7 to the left. This gives us y equals 2x minus 7. We immediately put brackets around this expression to protect it during the next step. Choosing which variable to isolate before you start writing prevents the arithmetic from becoming unnecessarily difficult later on. Now try to execute the next phase. Take our new expression for y, substitute it into equation 2, and solve for x. Here is the work. We have x plus 3 times the quantity 2x minus 7 equals 7. We distribute the 3 to both terms inside the brackets, giving us x plus 6x minus 21 equals 7. Combining like terms gives us 7x minus 21 equals 7. We add 21 to both sides to get 7x equals 28, which means x equals 4. Finding x is only the first half of the solution. To find the value of y, we need to perform what is called back substitution. We take our value of 4 and plug it back into our isolated equation. 2 times 4 is 8, and 8 minus 7 gives us a y value of 1. We now have a pair of values. X is 4 and y is 1. For this specific system, these are the only values that make both equations true at the same time. You can always verify your own work in algebra. A solution is only correct if it satisfies both original equations. Let's test equation 1. 2x minus y equals 7. Substituting our values, 2 times 4 minus 1 equals 7. The first equation balances. Now test equation 2. X plus 3y equals 7. 4 plus 3 times 1 also equals 7. Because these values work in both original equations, we have proven the solution is correct. We can consolidate this entire process into 5 distinct steps. First, isolate the easiest variable. Second, substitute it into the other equation. Third, solve for that variable. Fourth, back substitute to find the second variable. And fifth, check your result in both equations. To master this, you need to apply these steps to a fresh problem. Try solving this system. X minus 2y equals 1, and x plus y equals 10. Look closely at both equations to see which variable is the best one to isolate first. Work through the steps and leave your final x and y values in the comments. I will pin the correct solution so you can verify your work. Consistent use of this process allows you to solve for two unknowns, regardless of how they are paired together.